So, good afternoon everyone. My name is Peter, and during this session I will give you an overview of the new timber functionality that has been developed in Scia Engineer Release 2012. During this presentation I will show you first of all the document that you can see here, which is in fact the theoretical background which is used for the timber development, and I will of course also show you Scia Engineer itself, so you can specifically see the new developments that have been made. As most of you will know, within Scia Engineer we already had the Eurocode ENV check for quite some time now, and we now decided to upgrade it to the new Eurocode EN. In addition to that, not only did we upgrade the check, let's say, but we also added some new features, some new functionalities, which will gradually make also their way into other developments like steel development, aluminium development, and so on. Specifically for this webinar, should you have any questions whatsoever, you can always type them into the specific menus here in the webinar system. There is a questions system and there is a chat system. The best will be to specify your questions at the end of the webinar. We will of course leave the webinar open a little bit longer than the allotted time, and then we can discuss any questions that you might have. Okay. So that said, if we have a look at the new Eurocode EN, the new Eurocode EN has been published some time ago, and more importantly about it, the Eurocode itself is dated 2004, but much more important than that is the addendum that has been published, which is the one that I'm showing here, the addendum A1. This addendum in fact contains some quite important changes. More specifically, the changes are related to the shear check. In this addendum there is some indication how you can take into account cracks in the shear checks, and also a specific check, compression perpendicular to the grain, has been completely rewritten in this addendum. So it's quite important when you're looking at the timber check that you really take into account also this addendum. Several national annexes are taking this into account, but there are still some national annex publications which have been published, let's say, after the base code was published, but before this addendum has been published. And this causes some, let's say, discrepancy that these national annexes did not yet include the changes of this addendum. More than likely, those specific countries will make an update to their national annex soon enough. So, if we have a look then at the theoretical background for the timber design, as you can see here to the left side of the menu, where you see an overview of the different articles, the structure of this theoretical background is in fact in the same way as you know it most likely from steel and also from aluminium. The main idea was that in this theoretical background we provide you all the required information to understand how or what specifically was implemented in Scia Engineer. And I will walk you through this document during this session. So if we, for example, have a look at the consulted articles, there you can see an overview of all the possible or all the different articles which are currently supported by Scia Engineer. You can find a complete list with information about which article is supported, is there some additional information, and so on and so on. If we scroll through it, and first of all we, for example, have a look at the base of design and the material properties. The Eurocode itself does not give any material properties. The Eurocode EN1995 is just referring to the product standards, the material standards, and in case of solid timber this concerns the EN338. For glulam timber this concerns the EN1994. We have been going through these standards, especially the EN338 has received some recent updates, and all the latest materials or the latest solid timber kinds which were listed in this code have now been added into Scia Engineer. So if I switch specifically to Scia Engineer and I have a look, for example, in the material dialog for Eurocode EN, you will see that this is in fact a new list of materials. If you compare this to the ENV, there are some additional materials, I believe especially the D18, if I'm not mistaken. These were new in the latest version of the EN338 code. So these materials have been fully updated. As you can see, for timber there is not only the default E modulus, which is valid, let's say, for parallel to the grain. There is also the G modulus, but as you can see here, since timber is of course an anisotropic material, there are also some additional properties like the 5 percentile E modulus, which is listed here, the E modulus perpendicular to the grain, E90, And then we also have the different characteristics, the bending characteristic, the tension characteristic for, or the tension resistance for tension parallel to the grain or for tension perpendicular to the grain. And then a very important one, for compression, we have compression parallel to the grain and compression perpendicular to the grain, which in most cases, as you can see, is much more decisive, much smaller than the one that we have for parallel to the grain. This is of course a big, I would say, difference if we compare timber with other kinds of material like steel and aluminium, and this will also have its effect of course in the check. In addition to that, you can specify the type of timber. Currently we are supporting solid timber and glued laminated timber. You could also modify the properties so that you could, for example, execute the check for LVL and so on, but in most cases the general applicability is for solid and glued laminated timber. Okay. Now, what else do we have in the project dialog? Of course, as you know within Scia Engineer, besides the National Code, we also have the National Annex. So let's have a look in the National Annex library. Here you will see that now the National Annex library has been expanded with Eurocode 5, Design of Timber Structures. So if we have a look at the specific parameters for timber, by default, you can expect the safety factors here. So we have the safety factor for solid timber, glued laminated timber, and specifically for accidental combinations, because the Eurocode is in fact giving a specific coefficient for accidental combinations. Note also that at the bottom here in the description field you will find some more information. You will always find the reference article that has been used, a description and so on about this specific parameter. And a special one which is added here is in fact the modification factor KCR. Now this is a factor that was added in this addendum that I just showed. It's used specifically for shear to take into account the influence of cracks. Because of course if you have a crack in your cross-section, it means in fact that you have less material there, or as the Eurocode uses it, a smaller width in that case, and that will lead to a higher shear stress. By default, the Eurocode has a very simple method for it. They just give a coefficient like 0.67. However, in some national annexes, there is a complete calculation method being done. For example, in the German national annex, the Austrian, the French, and so on. They have special methods to be taken into account, and this is what can be selected here. I'm using the default Eurocode, so I get information that is the factor for taking into account the influence of cracks. If I would switch to any other national annex, for example the German national annex, then you will see that the specific German method will be used here. So this is an overview of the national annex parameters which are of importance. Now, other than that, before we start with the actual check itself, we of course first have to do an analysis. We first have to do a calculation. According to Eurocode 5, the calculation can be done in different ways. The same like in steel, for example, you can do a first order calculation or you can do a second order calculation. However, for timber, this difference is quite important. The Eurocode, in fact, specifies the following. If you do a first order linear elastic analysis, then you can use the mean values for the stiffness properties, the mean value for the E modulus and the G modulus. If you, however, execute a second order analysis, then you have to use design values for your stiffness properties. A design value means you have to take the mean value and divide it by the respective safety factor. So this means, and this is also the way how it's taken into account in Scia Engineer, if you have a project in which you combine both solid timber and glulam timber, since both of them have a different safety factor, it means that the different safety factors depending on the beam will be used during the second order analysis. So this is quite an interesting change, let's say, or quite an interesting difference from steel. Those of you familiar with steel will know that this rule in fact is not that new. In steel this is, for example, also used in the DIN code. So now it finds its way also in timber. Okay, so this is fully automated, automatically implemented within Scia Engineer. Except this, so this type of analysis, if you execute a second order analysis, then as you know from the different Eurocode parts, the Eurocodes most of the time also indicate the use of global imperfections and local imperfections. Also these have been implemented according to Eurocode 5. So if I have a look, for example, in this project, and I make sure that my nonlinearity functionality is activated. In the library for initial deformations, this is where in the past you were able to define a global imperfection for steel and for aluminium. There you can now also define a global imperfection according to the code for Eurocode 5. What you might notice here, for those of you familiar with this dialog, in previous versions of Scia Engineer regarding steel and aluminium, for example, we always call this according to code. So we called it manual input, factor, or according to code. But the question then is, which code? So now we have modified these strings so that it's clearly identifiable. In this case, since I activated timber material, I'm inputting an imperfection according to Eurocode 5. In the same way, if you would activate multiple materials like steel, aluminium, concrete, and so on, this combo box will be expanded with multiple options. I can show it also later on for those of you who are interested. It will be expanded with multiple options that you will really see imperfection according to EN1995 or 1993 or 1999 and so on. So this is now fully implemented, the imperfection. I can also show you, for example, the respective article from the code. Here, where you can see how the imperfection is defined. In the same way, the Eurocode 5 also defines a bow imperfection. This is easier than steel. In steel there is of course the whole story with plastic and elastic analysis, while the Eurocode 5 is just giving one fixed value independent of the type of cross-section and so on. And this can be set in the same way in the buckling data as you know it from other materials. Using the buckling and relative lengths, I can open the buckling data, and in the buckling data I can specify that I would like to have an imperfection, again according to this article. So here also an update was made to strings, no more according to code. No, there is a real indication which code, which article is being used so that it's completely clear. Okay. So this is an introduction, let's say, regarding the analysis. So these options can be set, and I think the most important is what I indicated with the stiffness property. So if you execute a second-order analysis within Scia Engineer, then automatically these design values will be taken into account. Now, other than that, timber is also, let's say, a material which is a natural material, so it's also being influenced by environmental influences. And this is something that we will have a look at now. An environmental influence in the Eurocode is in fact defined using a specific class. You can specify class 1, 2, 3 in the Eurocode. And let's have a look how this is defined within Scia Engineer, where we can find the service classes. Now, in this tree of Scia Engineer, I go to the timber service. And this service will be familiar to most of you. It follows the same logic as the default steel tree, for example. I will now open the timber setup. And in the timber setup, we can find some more general settings which are being used for the timber check. I just indicated the environmental influences. We have been using the same titles here, in fact, as the articles used in the Eurocode. So the Eurocode specifies that as an environmental influence, they define a service class. This class takes into account possible effects of moisture content on the different properties of the timber. So during using this combo, you can select any of the given service classes. This in turn will have an influence on the specific K-mod coefficient, the K-mod, the modification factor. This is in fact the coefficient that will modify your strength properties. Now, these properties are in fact let's say fixed by the Eurocode. So for solid timber as well as for glulam timber, these properties are fixed. However, in our previous Eurocode ENV, these properties were editable in Scia Engineer, and this allowed the user to make modifications if necessary, or if you wanted to, for example, use LVL, you could modify these values. For that reason, we still kept this logic. So if I open the table for K-mod, you will see that by default we are providing for the different load durations and the different service classes the K-mod coefficients, both for solid timber and for glued laminated timber, but these values are editable. You are able to make modifications to them. For example, you can use these values. Should you wish to go back to the defaults, we have provided a load defaults button that you can go back to the default values. Okay. So these are the specific K-mod values which are being used by the ULS check, the ultimate limit state check, to modify your strength and stiffness properties. Another specialty, in fact, in timber is the so-called depth factor. Now, what is in fact the depth factor? And the best way to explain this one is also to directly show it in either in the Eurocode or in the theoretical background. So I can show it here in the theoretical background. The Eurocode in fact states that most of the or several properties which are related to tension and bending, so the tensile strength parallel to the grain and the bending strength, they have in fact been derived using specific cross-sections with a width of 150 millimeter. And the Eurocode then indicates if your actual cross-section, your actual rectangular cross-section has a width or dimension which is lower than 150 millimeter, then you are allowed to increase your tensile and or bending strength. And the increase is quite significant. As you can see in this formula, we can increase even 30%. So this is quite a lot. And therefore it's definitely beneficial to take this depth effect into account. This depth factor is therefore activated by default. As you've seen here in the setup, apply the depth factor is applied by default. It's of course also shown on the output. We can have a look at it later on when we look at the detailed output. You can find some more information here. Again, the reference article is being given. What it does, it takes into account the member size on the strength and so on. Should you, for a specific reason, not wish to take this into account, you can of course deactivate it. So that is why we made it as an option. The next option you see here, which is, let's say, quite special in fact for timber, is the contact length, which is used for compression perpendicular to the grain. In theory, if you have any point load, let's say, or any jump in a shear force on your beam, you have to take into account this specific check, compression perpendicular to the grain. Now, of course, in reality, point loads do not exist. There is always some small width, let's say, over which a point load works, and this is in fact this contact length, contact width that you can specify here. This value is editable. You can also modify it for each point load separately, and I'm not only talking about point loads, but mainly also about supports, because also a support reaction will cause this compression perpendicular to the grain. For those of you familiar with steel, compression perpendicular to the grain in timber is completely the same like the local transverse forces check in steel purlin design, or web crippling check as it's called in the American code. It's completely the same principle, that you have the shear force which is in fact causing compression perpendicular to the grain of the timber element. This was completely modified in the addendum. So the check which is now implemented in Scia Engineer is really the latest version according to the addendum A1. The other options that you can see here in this setup are in fact the same as you know them from steel or aluminium. You can specify the default sway types, you can specify the max values for the K ratios and so on. You can optionally indicate a maximal slenderness value. By default it's 200, but you can modify it if you do not wish to take this into account. Also the use of second order buckling ratios, if you want to indicate that, for example, all buckling ratios are 1, in that case that the system length should be used instead of the buckling length, is all here. And also these options, for example, section check only if you do a full second order analysis, or if you do a second order analysis with imperfections that you only want the lateral torsional buckling check to be executed. All these options are available here. Completely the same like we have them in steel and aluminium, for example. Let's have a look then at the second tab, where we have here the serviceability limit state. Now, for serviceability, timber is in fact again a little bit a special case, because timber takes into account the creep, the effect of creep on the deformation. Now, this effect of creep is being taken into account using the so-called K-def deformation factor. Now, in this K-def deformation factor, it follows the same logic as K-mod. You can again open the table, make any modifications that you wish according to the material and the service class, and if necessary, you can always load back the defaults if you want. You will also see a special option here, which specifies that increase K-def according to this specific article. The article is also listed here, which says that if timber is installed at or near its fiber saturation point, and it's likely to dry out under load, then you should increase the K-def coefficient by 1. If I have a look at my kdef values, I see, for example, 0.6, 0.8 here. If I use this option, then you will see that these values have been increased by 1, and also a specific note is added to indicate that these values have been increased. So all this is nicely linked. You can nicely retrieve it here. In addition, as you know from other checks, within Scia Engineer we are doing also a relative deformation check. The relative deformation check for timber does not only include the initial deflections, but also the final deflections, including creep. So also this creep is being taken into account. This means also that we need two limiting values. We do not only need to limit the initial deflection, but also the final deflection. So if I use or open the table here, then you will see that for each of the different structural types, you can specify both the limit for the instant deflection and the limit for the final deflection. These are in fact the most important options for the setup. The buckling defaults is totally the same as for the other materials, so these ones I believe you will know also from the other materials, so there is no modification there. I think the biggest or the most important parameters are of course the service class, the kmod and the depth factor kh, and here of course the kdef. Let's have a look then at the check itself, and perhaps before I go to the check, one more thing which is not new, but just to indicate that you know where to find this parameter. You have seen in the setup that the kmod coefficient is dependent on the load duration. If you input any load case within Scia Engineer, any variable load case, so action type variable, you are able to specify the duration. This is not new, this is there already for quite a long time because it was used also in the Eurocode ENV. But this is just to show you where to find it, so you can specify a long, medium, short, instantaneous. These items can be indicated here. If I again go to the timber service, what else can we find here? So if we have a look at the check now, the ULS check, I will first do a brief check, and if I now refresh, then I get my output. I see in red that something is not okay, so we will see how we can fix that later on. And I can also launch the preview. Now, a quite interesting improvement which we have made, if you compare this to, for example, the output of the steel check or the aluminium check, is that in addition to showing the unity check value, we are now also both graphically and numerically showing a warning. We call it error warning nodes. This is something which was already used within Scia Engineer in the concrete check, and it indicates to the user that there is some warning there or some error, there is some issue. And imagine that, for example, in steel, if you would like to see such messages, you always need to have the detailed output. But many users are just using the brief output to get a general overview, and even now in the general overview we are indicating that there is some problem there. Now, what is it? How can I see what actually this message means? Therefore, I can activate here the same like in the concrete menu. I can activate print errors warning nodes explanation. And then I will get an indication that says this is warning number 2. Warning, the slenderness is larger than the limit value. I've just shown you the slenderness limit in the timber setup. This is an issue which is happening here. And of course, if we now want more information, we will have a look at the detailed output. So if there is any error or any issue, like a check which is not being done for some reason, or a special formula that is being used for some reason, and so on, it will now show itself through these specific settings here, showing there is an error, a warning, or a note. If you would like to make a print output and say, I do not want to see this on the output, you can always deactivate it in the drawing setup. There is an option here that you can say errors and warnings. Either I don't want to see them, I want to see errors and warnings, or I in addition also want to see notes, for example. Alright. Now let's have a look at the detail check. So I will switch the output to detail. So you see the rest of the menu is totally the same like the existing checks within Scia Engineer. And if we have a look at the detailed output of the timber check, this will look familiar. It has the same structure, the same logic as being used in steel, for example. At the top you get an overview of the beam, the type of cross-section used, the material, which combination has been checked, and then the final unity check. You see here the safety factor. Now, if you remember, there were more safety factors. We also had a safety factor for glued laminated timber and for accidental combinations. This is automatically filtered out. So on the output, only the safety factor which is actually used for this member is being shown. An overview of the material properties, the critical check with the internal forces, and then I believe a very important table that shows the modification factor. This is quite important since it prints not only the service class but also the load duration, because as you know, if you have a load combination with multiple load durations, of course only one load duration can be used as specified in the Eurocode, and here you can nicely see which load duration has been used and which is then the corresponding K-mod coefficient that is used. Then you get an overview of all the checks, for example, compression parallel to the grain, the bending check, and so on. So all these checks are being listed here. The same format as what you know with steel, so always the article is being listed, which formula has been used, all the intermediate values are printed, and the final unity check. As you can see here with the bending check, some additional data is being printed. The bending check for a rectangle has this specific Km coefficient, which takes into account the interaction of both directions, and then we get the unity check according to these two formulas and so on. If I switch now, just for the time being again, to the theoretical background, let's have a look at the bending check, for example. If I look in the theoretical background for bending, there you will see the background indicates we are doing this check according to this article. It will only be done in case there is any moment present. If you have a rectangular cross-section, then we will use the coefficient Km, and then of course the question is, what is a rectangle? And this is then also specified here if you have form code 7, or if you have a geometrical rectangle or a rect of type timber. These are cataloged as rectangles, and for these we will use the Km coefficient. So all the detailed information can be found in this document. It specifies exactly what we do in which case. Let's have a look in the Eurocode itself, the article 616. And here you see the bending check, which then specifies the formulas, formula 611, 612, and both of them can then be retrieved also on the output. Okay, so this is just to give you an idea about the check itself. As you can see, all the different checks according to the articles 6.2 and 6.3 have been implemented. For example, the buckling check, which in the Eurocode is specified as column subjected to compression or combined compression and bending. This table will be familiar from steel, for example. You start with the sway type, the system length. Using the buckling factor, you calculate the buckling length. This will give you the slenderness, which can be recalculated to a relative slenderness. This is compared to a limit slenderness, and since we exceed this value, we have to calculate some imperfection. And finally, we can calculate what you know from other codes, the Chi value, which the timber check in fact calls the Kc value. It means we can only, or we have to reduce our compression resistance by either 40% or here only 7%. And then finally, we can execute the check. Since timber does not give any, let's say, combined check, they directly give the combined check as part of this buckling check. You will see both formulas listed here. And this is, by the way, also the location where this note was coming from, or the warning that we saw earlier, that the slenderness was exceeding the limit. The limit set in the setup was 200, and here we see that the slenderness of 207 exceeds the limit, so that is why we got the warning previously. If I show this same check, for example, in the Eurocode, so here we have columns subjected to compression or combined compression and bending. The calculation of the slenderness values is detailed here. The checks values that we have seen, and then all the intermediate values are being listed here, how to calculate the beta C value, and so on and so on. So all this information can be found in the output. Then we have the final one, the LTB check, in fact, where you can also see all the details, the critical moment that has been calculated, the load position, as you know also from steel, stabilizing, destabilizing, and so on. All these items are also being shown here, again with specific reference to the Eurocode. Okay. So this was a general overview of the ULS check. One special check which is not printed here, but which I definitely would like to show you, is the compression check perpendicular to the grain. So I will close my preview. If we have a look at this beam, for example, the beam is loaded by a line load, so definitely we will have a jump in the shear force diagram at the endpoints. So let's have a look. If I execute the check only for this beam, so selection current, and I only execute the check for the sections at the ends, then I of course get a high check here. So let's have a look now at the output. So at position 0 meter, as expected, we have a shear force there. And now you will see the specific compression perpendicular to the grain check. And so here you get more information what this check is in fact doing. The check is taking into account this jump in shear force diagram, then using the contact length which was set in the setup and the width of the cross section to calculate the area which is loaded, let's say, by this compression force. This leads to a compressive stress perpendicular to the grain, and this is then finally checked using some strength increase factor KC90 to finally do the unity check. So this is just to show that also this check is nicely taken into account according to the latest correction sheet. Alright, so this was information regarding the ULS check. Now let's have a look, for example, at the SLS check. First of all, before we go to the SLS check, let's have a look at the theory, and I will show it here in the Eurocode. The Eurocode in fact indicates the following. The Eurocode specifies that if you calculate a deflection check for timber, not only do you have to check the initial deflection, you also have to check, or the instant deflection, you also have to check the final deflection, which includes creep. Now, how is this creep taken into account? And this is in fact a quite big difference from the Eurocode ENV. The Eurocode ENV just used this formula. The ENV said for any load case, you just increase the instant deflection by the value 1 plus kdef. So if kdef was 0.6, you have to increase it by 1.6, for example. The big difference now with the Eurocode EN is that it has been split depending on the type of action. Permanent load cases still follow this rule, but for a leading variable action, you have to take into account this modification, while for an accompanying variable action you have to take into account this modification. And this is quite a big change. This is implemented, of course, in Scia Engineer, fully automatic. So if I now execute the deflection check, the SLS check, including creep, I will in fact get for each direction two checks or two values. I will get the instant check and I will get the final check, which takes into account this additional creep effect. Let's have a look. If I switch to the SLS check relative deformations including creep, the check is being executed, and as you can see on this table shows us both the UY deflection and the UZ deflection. I will focus on the lower row, which is in this case the UZ deflection. I see a UZ deflection of minus 46 millimeter instant deflection, which is done for my SLS combination. This is the characteristic SLS combination which I've used. This is calculated as the following value relatively, which gives us a unity check of 2.32, for example. The final deflection, which includes creep, is much higher. You see here we have minus 46, here we have minus 68. The unity check done is this one. So here you see, in fact, you have for each section, you have 4 unity checks. For Y instant, for Y final, for Z instant, and for Z final. The, let's say, limiting unity check, the highest unity check of these 4 values is the unity check which is being shown here and also being printed there. So this table has also been modified. If you compare it with the old ENV output, you can now retrieve all the information. Also kdef is being printed here, and so on and so on. Okay. Some other special items or specific things. Of course, the auto design, which you know from steel, for example, is still valid for timber also. So if I have a look at the ULS check, I can launch the auto design. You will switch the filter to cross-section, in my case my rectangular cross-section, and I can use in this case the sensitivity auto design. Sensitivity auto design, which means I will not just optimize one parameter, I will let the program determine by itself which parameter is best to be optimized. So I use the advanced auto design. I want to optimize both the width and the height. I let them go in steps of 10 millimeter, for example, and I just search for optimal. And as you can see, automatically Scia Engineer determines the best width, the best height that should be used. In each step, he automatically modifies the parameter that has the highest influence until my unit check is as good as 1. Since I now modified my cross-section, I of course get a message that I should recalculate my structure. So let us recalculate. Now I can refresh and I get my new optimized check, and more than likely also the SLS check will now be nicely green, 0.82. Okay, so this is just to show that also this functionality regarding the auto design is still valid, is still also valid for timber, is also used here. What else do we have here in the service? We have some specific timber member data, the same like steel member data, for example. There is something quite special in here for timber, which is the so-called system strength. Now, the system strength is something which is given in Article 6.6 of the Eurocode. I will open also the theoretical background. So in Article 6.6, there is an indication that says, well, if you have equally spaced similar members, which are laterally connected by a continuous load distribution system, in, let's say, freely translated, this means if you have a floor system with some floorboard on it, for example, then you can take into account this K-sys coefficient. And you have to see it as a coefficient that increases the strength of your beam. So in this case, if I would imagine that this is a floor system with 3 floor beams, they are connected by some kind of plate, for example, I could take into account an additional system strength of, for example, 1.1. So this means I get a 10% strength increase, which is quite significant. Now if you start adding this with the KH depth factor that we've seen before of 1.3, you get quite a significant strength increase using these coefficients. Other than that, we have the default data that you know from other materials, the member buckling data to overrule the member data, for example, the member buckling data on a specific member. LTB restraints, which are then being taken into account in the LTB lengths, and also specific compression perpendicular to the grain data. As I indicated before, this is totally the same like in steel, the transfer forces check or the transfer forces data, by which you can modify this data specifically on the beam. So here also in timber, I can specifically modify the data which is used for the compression perpendicular to the grain check and indicate that, for example, I want to specifically on a certain position modify the contact width or modify the contact length to indicate that the length has to be modified there, or I can change support condition. The code gives different formulas if you have discrete supports or if you have continuous supports and so on. So this can also be manually overruled wherever you want on the beam. And then finally we also have the slenderness data, which of course shows the slenderness information that you know from other materials, the system lengths, the buckling ratios, the slenderness values, and so on. Specific here in comparison to steel is that also the E0 values, if they are used, they will also be printed here. Here I'm just doing a linear analysis, so I have no E0 indicated, so I see no values. But if you set them, then these values will also be listed here, so you can check them. All right, so this is about it. This is let's say the general overview of the timber check according to Eurocode 1995. Within the theoretical background, you can find then more information about each check, as I showed. So all the information is here, which articles are supported, and so on. You can also find, for example, if I go further into this depth factor, there is more information about when we use a specific formula, There are some notes, what do we do in a certain case, and so on and so on. So all this information can be retrieved here. There is also a specific manual theoretical background, in fact, for national annex settings, as I indicated during the introduction. If you, for example, switch the national annex to a different country, if I switch it, for example, to Germany, then you will see that specifically for timber, we are now using the German method to calculate the KCR value. So in that theoretical background, you can find more information about this method, what it does, and so on. Specifically for Germany, you will find out that also some additional checks are being done. In the German National Annex, there are some more checks that are being given, so also that has been implemented, and you will see them also on the output. Okay. So this is about everything which I wanted to show you. Just for information, in the next release, so release 2013, the timber check will be expanded even more with special checks for single taper, double taper, and curved members. So that is the next step in the development. So in the release 2013, the check will be further expanded with these special checks. So with this, I would like to conclude my presentation. Are there any specific questions which you would like to ask? Normally you can type them into the setting, and I see there is already some questions here, so you can type them into the different boxes. And I will also see if I can activate your microphones, because I believe they are still muted all. Okay, so I'm now unmuting the different microphones. So if anyone has a question, please type it in the setting, or you can ask it directly or put it on the chat window. And I see some questions have came in. I will perhaps answer them for the entire group. One question is, are there any benchmarks available for timber design? Yes, there are benchmarks, and normally they are already available on the website. So benchmarks are already available. They can be found on the website normally. I will perhaps ask Astrid to later on also publish a link to that one. And so regarding the curved members, that is planned for the next release, in fact. So for the next release 2013, they should be there. Yes, normally there should be in the secured downloads, but I will check it to specify exactly what the path is where they can be, where these benchmarks can be found. Okay, thank you very much. At present, so the present checks, in fact, are purely member checks, not connection checks. For the moment, we have, let's say, an agreement also with our partner within the Nemetschek group, Freelo. Freelo, they have a specific module for timber connections. And that will also be the idea that for timber connections, this module from Freelo can be used. Of course, in the future, we can further elaborate on this, or we can further see if any link or automatic linking with the Freelo program should be made. But at present, the Freelo tool can be used for it. So the current development within Scia Engineer is purely for member checks. Alright, so any other questions? You can just type them into the question window. And if there are no more questions, then I believe we can close this webinar session. I would definitely like to thank you all for your attendance, and definitely, should you have any questions later on, you can always send them also to any of the addresses that you have from Scia, either to info or to support directly, and then we will definitely get back to you with an answer. All right, so thank you very much, everyone, and have a nice afternoon.